You ever seen a lizard just basking in the sun, looking all lazy, and then suddenly, poof, it's gone? But a cold one seems like it's moving in slow motion. Well, it's not just about getting a good tan. The answer is actually all about chemistry, something we call chemical kinetics.
And that's exactly what we're going to break down here, the speed of chemistry. We're diving into the world of chemical kinetics, which is really just a fancy way of asking a simple question. How fast does stuff happen?
And believe me, this isn't just for lizards. This is the science that explains why a cake bakes in like 30 minutes, but a bridge can take decades to rust over. It's what controls how our bodies use food for energy and how long the battery on your phone lasts. It is all about the speed of chemical change. Okay, so first things first, let's get on the same page about what we even mean by the speed of a chemical reaction. The official term you'll hear is reaction rate. And you know what? It's just like any other rate you're already familiar with. Your car's speed is distance over time. Your wage is dollars per hour. Well, a reaction rate is just the change in the amount of stuff over time. How quickly are our starting ingredients, the reactants, disappearing? Or how fast is our final product appearing? Same idea. And this is exactly like driving a car. You know how you can calculate your average speed for an entire road trip? That's one number. But your instantaneous rate, that's what you see on your speedometer, right? And it's changing all the time as you speed up or hit the brakes. Chemical reactions are just like that. Their speed is almost never constant from start to finish. Look, here's a perfect real-world example. This is hydrogen peroxide just breaking down on its own. Notice how in the first 6 hours, its concentration gets cut in half, a huge drop. But then, look at the next 6 hours. It slows down a lot. The reaction is basically running out of fuel. The main takeaway here is that reaction rates change. They start fast and tend to slow down over time.
So that leads to the really big question, right? If these speeds are always changing, what's controlling them? Are there like knobs we can turn to speed things up or slow them down on purpose?
And the answer is a big yes. There are basically 4 main control knobs we can play with: the physical state of the stuff we're mixing, how much of it we use, the temperature, and, the special one, the presence of a catalyst. Let's just touch on a couple of these to see how they work. First up, physical state. This is all about surface area. I mean, for two things to react, they have to physically touch each other, right? So the more contact they have, the faster the reaction. It's why a pile of sawdust, with all its tiny particles and massive surface area, can go up in a flash, while a giant, solid log just kind of smolders for hours. It's the same wood, just a different shape. And then you've got temperature. This is the secret for our lizard. There's this incredible rule of thumb in chemistry that for a ton of reactions, just raising the temperature by 10 degrees Celsius, that's about 18 degrees Fahrenheit, can actually double the reaction speed. That is a huge, huge effect. And it's exactly why that warm lizard's metabolism is running on overdrive. Okay, so we know what can change the speed, but why? Why does temperature have such a massive impact? To get that answer, we've got to zoom way, way in, down to the molecular level, and uncover the secret of collisions. It's all based on something called collision theory, and it's actually pretty simple. For any reaction to happen, 3 things have to be true. 1, the molecules have to actually run into each other. Duh, right? But 2, they have to hit in just the right position. And 3, they have to slam into each other with enough force. That orientation part is absolutely crucial. I mean, look at this. If a carbon monoxide molecule gets hit on its oxygen side by another oxygen, they just kind of bounce off. Nothing happens. It's a dud. But if the carbon atom is the one that gets hit, then bam, everything's lined up perfectly to form a new bond. It's like a key fitting into a lock, and only works one way. So we have the collision, and we have the right orientation. Now let's talk about that third rule, the most important one of all: colliding with enough energy. This idea is so important, it gets its own special name. It's called activation energy. You'll see it written as EA. And all it is the absolute bare minimum amount of energy you need to make a reaction happen. It's the energy barrier, the price of admission that every single reaction has to pay. The best way to visualize this is to think of an energy hill. Imagine your starting chemicals, your reactants, are sitting in a valley, and the final products you want to make are in another valley on the other side of a big hill. To get there, those reactants have to be pushed all the way up and over the top of that hill. That peak is the activation energy.
Only then can they roll down the other side and become products.
And here is the kicker. At any given moment, only a tiny, tiny fraction of all the molecules zipping around in a container actually have enough energy to make it over that hill. This is why not every collision works, even if the orientation is perfect. Most of them just don't have enough oomph. So this energy hill is the biggest bottleneck, right? It's what keeps most reactions from happening instantly. But what if? What if there was a shortcut? This brings us to that fourth control knob we mentioned, the catalyst.
I mean, is there a way to kind of cheat to get from the reactant valley to the product valley without having to climb that enormous hill every single time?
Well, yes, there is, and it's called a catalyst. A catalyst is this amazing substance that makes a reaction go way faster. And here's the magic trick, it doesn't get used up itself. It's like a chemical matchmaker. It helps the reactants get together, and then it just walks away, totally unchanged, ready to do it again. So how in the world does it do that? Okay, let's go back to our hill analogy. The normal path, without a catalyst, is to climb all the way over that tall mountain peak. What a catalyst does is it provides a completely different path. It's like it builds a tunnel straight through the mountain. The journey through the tunnel has a much, much lower peak, a lower activation energy, which makes getting to the other side way easier. And by lowering that energy barrier, now a whole bunch more molecules have enough energy to make the trip. Suddenly, way more collisions are successful, and the whole reaction just takes off at an incredible speed. This is literally how enzymes in your body work. They are nature's perfect little catalysts, making the reactions of life happen fast enough to keep you alive. And that really brings us full circle. This quote sums up everything we've talked about perfectly. Chemical kinetics is about two things. One, measuring the overall speed of the reaction, and two, understanding the tiny molecular story of collisions and energy that actually makes the whole thing go. So, now you know the four control knobs for chemistry: surface area, concentration, temperature, and catalysts. I'll just leave you with this to think about. What's one process in your life, from cooking food to maybe even learning something new, that you wish you could speed up or slow down? Thanks for tuning in.